Okay, thanks very much, Adam. I'm very grateful to be awarded I didn't know it was an award either. It's a real pleasure to give this talk. I'm going to talk about this Indonesian earthquake hazard project that we've been involved in for about 7 years now. And although my name is the only one on this slide, there are really many people who contributed to that. I want to particularly mention Hadi Gassemi, Jonathan Griffin, David Robinson, Trevor Dew, are people who have been very actively involved in that. And there have been others also who have been involved in the management. And I'm looking at Ricky Weber back there, who's been after us for reports and things like that. Yeah, there have been a lot of people involved in that, as well as my colleagues at ANU, Simon McCluskey and Ashraf Kalali and Paul Tigroning. I wanted to start off by talking generally about seismic risk in the Asia-Pacific region. This is just a plot of population in the Asia-Pacific region. As we all know, it's a very heavily populated area. It has about half the world's population living in about 22% of the world's global land area. And you can see that in parts of the Asia-Pacific, there are particularly high concentrations of populations, in particular along the Himalayan arc. And then along the Sunda arc here, as we'll see in a few slides later, there's particularly high concentrations in Java, as well as the Philippines and East Asia. And these often correspond to hotspots of earthquake activity. There's the Himalayan collision zone up here, which can cause and has caused very large historical earthquakes, as well as very large earthquakes along the subduction zone, along the Sunda arc, as well as not so large but very dangerous earthquakes in the active crust landward of the subduction zone. And the same is true over here in the Philippines. So we can see that in many cases, these areas of very high seismic activity coincide with various areas of very dense population, such that there are 480 million people in the Asia-Pacific region who live in areas of high to very high seismic hazard. But you wouldn't know it in some cases if you lived in these regions, in particular in Indonesia. If you lived there throughout the 20th century, Indonesia only suffered about 2,400 casualties due to earthquakes and tsunamis, a remarkably small number given recent history, as well as given the history prior to the 20th century. But then, of course, on 26 December 2004, suddenly they suffered 167 casualties in one event. Similar things can be said elsewhere, like in Haiti. This is a pair of slides from some people who gave a talk at one of the GEM meetings I attended. And this is some of their slides, actually, in which they made the point that in Haiti, fewer than 10 people died in earthquakes during the 20th century. But then suddenly in 2010, more than 200,000 people were killed in a single event. And the point they were trying to make, and that I'm trying to make here, is that we need to measure progress in disaster risk reduction. And we can't do it by just looking at the disaster loss data. You can't say, you would have said up until December 2004 that Indonesia and Haiti didn't have a problem really with earthquake risk. But obviously you would have been wrong. So we need to find other ways to measure what the hazard and the risk are, and then understand how we can reduce them. This high risk is not simply due to the fact that there are large populations, but that many of the people there are concentrated in megacities. Between 1980 and 2010, just 30 years, the region's cities grew by 1 billion people. And half of the Asia-Pacific population are now living in urban areas. By 2050, it's estimated that 2 out of 3 people will be living in urban areas. And the Asia-Pacific region has 17 megacities, including 3 of the world's largest. So it's a huge concentration of very large cities that have grown up very recently, and in some cases during the 20th century, in places where we had few earthquakes that we know are seismically active, but have had few earthquakes during this time of very explosive population growth. Nowhere is that more true in Java. Java's current population is 145 million. 57% of Indonesia's total. Java is one of the world's largest islands, and at the same time, it is the most densely populated island on Earth. There's a high rate of poverty and a high rate of urbanization. So, and you can see in this figure here, the urban areas of Java are in yellow there, the current areas of urban extent, and that's projected to grow. It's not, the urbanization of Java isn't slowing down. It's projected to encompass all of the red area by 2030. And you can see that these urban areas have a variety of construction types, from very seismically non-resilient residential construction, as illustrated in the upper right, to high-rises, as illustrated in that figure to the left there. Indonesia, actually, Jakarta in particular, has quite a high proportion of high-rises. It really ranks among the top cities with a high population of very tall buildings, much more so than Mexico City, for example. And that will be an important factor later on in the talk, as we'll see. So we've seen these, since 2004, we've seen these what are called black swan events. This is actually from a GA presentation in which they're called black swan events, in which the impact was much higher than had been expected based on living memory. We've seen that 2004 Indian Ocean tsunami, 2010 Haiti earthquake, and 2011 Japan earthquake and tsunami. When and where will the next one occur? Well, there are actually many candidates in the Asia-Pacific region for earthquake and tsunami disasters. Dhaka, there's a large declement that has been recognized now as accumulating seismic strain energy right beneath Dhaka, huge city that's located on a very thick sedimentary basin. Manila has the West Valley Fault. GA has done some work on that area, running essentially right through the city. There's the Himalayan collision zone, which has been studied for a long time and clearly is a threat to major population centers in northern India. And then, of course, Jakarta, Surabaya, and Bandung in Java. Some seismologists regard a 1 million fatality earthquake as inevitable. It's going to happen someday and could well happen this century. So with all that in mind, and particularly the 2004 disaster in mind, the Indonesian Earthquake Hazard Project was started, and it's sort of started in was conceptualized in 2010, didn't really start work until 2011. It was funded by what was then called AusAid, part of DFAT, now called Australian Aid. And we also got some funding from the Australian Research Council. It was a collaboration between many Indonesian organizations and Australian organizations, so I'll mention them in the next slide. There were some core research areas that we wanted to improve our knowledge in the sources of earthquakes, as well as earthquake ground motion, and we wanted to build the capacity of Indonesians to do probabilistic seismic hazard analysis in order to support building codes. Because I guess one slide I don't have in here is one about the building codes. Really, better buildings are the only way we have to reduce earthquake fatalities. And in order to design appropriate building codes, we need to understand what the hazard is. But that's difficult in an area like Indonesia because the tectonic environment is very complex. It's got a huge number of active plate boundaries. Many of them actually, our knowledge of them is changing as we speak, and I'll mention some changes in the sort of our knowledge of that later in the talk. But you can see that there's a huge amount of subduction zone plate boundary, as well as major crustal faults. The Sumatran fault is bigger than the San Andreas fault, and also the Palu Coro fault has another strike slip fault with a huge slip rate. So they're both many subduction zone plate boundaries, as well as major crustal faults that we need to worry about in Indonesia. So it's going to be a very difficult thing to come up with credible seismic hazard assessment in such a complicated tectonic environment. And to do that, we need friends, we need partners. And I spent a long time on this slide. Actually, I screwed up on the last bit, which should only appear at the end. But this is all the partners. It was a very, very complex project in terms of partners. There were quite a few of them. And so I'm going to describe them actually individually. Bandung Institute of Technology is the premier technical university in Indonesia. So that's where much of their academic seismological expertise is, and they're able to do education, which was important for this project. Indonesian Institute of Sciences is, well, that's what the name implies, but it's got some of Indonesia's best seismologists who can give us information about the active faults in Indonesia. ANU, of course, similar to ITB, we partnered with ITB in both an education and research program involving mainly linking our seismological expertise, but also building capacity among some of the Indonesian scientists in seismology as well as earthquake hazard and risk. Agency of Meteorology, Climatology, and Geophysics. That's like the Indonesian, it's almost like Geoscience Australia and the Bureau of Meteorology rolled into one. It's called BMKG. They run the tsunami warning system and do earthquake monitoring and other things. The Geological Agency, that does the sort of, I guess what you could, it deals with licenses. It deals with the exploration companies and sort of pre-competitive information, things like that. But it also deals to some extent with geological hazards. And then Australian Aid, of course, they helped us with the funding. They funded it, and some of our staff were actually essentially seconded to Jakarta to help manage the project. So they were also, there was a lot of funding. And there was a lot of funding came, of course, both to GA and ANU from DFAT Australian Aid. And then, of course, the National Disaster Management Agency, BNPB, they were sort of the major partners of GA in the country. And they were the ones who partnered in the facility, which was originally called the Australian Indonesia Institute for Disaster Reduction, or Facility for Disaster Reduction, is now called DM Innovation, for Disaster Management Innovation. They were our main partners in this endeavor. I didn't actually work directly myself much with BNPB, but they were always in the background, and they had to sort of approve everything we did. Public Works in Indonesia, they're responsible for the building code. They've got a lot of civil engineering expertise and geotechnical expertise that was very important for us in developing the hazard map. And then a lot of these agencies eventually joined together, and I'll discuss that in the next slide, in what is now called the National Center for Earthquake Studies, PUSCEN. So that's a sort of consortium of many of the, I think essentially all of the agencies I've mentioned. We also worked with Global Earthquake Model Foundation, which we're all, at least most of the hazard people here are familiar with, that have developed state-of-the-art seismic hazard software platform that we could use for this project. And finally, we worked closely with the Geospatial Information Agency, BIG, in Indonesia. They're the ones who run the GPS network, and we did a lot of work with them in trying to characterize active faults. So I want to dwell on this a little bit. It's a very, what you can see, I didn't sort of highlight the Indonesian agencies, but there's at least 6 Indonesian technical agencies, I think, that we worked with. So it's a very complicated space. And the first thing we had to do was try to figure out who did what and try to work out, how we could give them roles in this project. And the interesting thing, in retrospect, the really interesting thing about that was that they had apparently never thought about working together before. I mean, I'm looking at Jono, I think he's nodding there. We went to them and we were all doing somewhat different things. They overlapped a bit, but it became apparent after a while that they really hadn't thought about working together to do this kind of thing before. And our concern was simply to get the project done and to get them working together on our project. But this really turned out to be perhaps the most important contribution we made, actually. I'll talk all about the science, but actually getting these guys to come together and work together towards a common goal was a new thing for them. And I think they regarded it as the most valuable thing that we did for them while we were there. And just to illustrate that, we at some point, I don't know if Trevor Dew is in the audience, but he got together the heads of all of the major geotechnical or geoscience agencies in a meeting, and it was the first time they had done that. They had never gotten together to talk about earthquake science in Indonesia before. And they all said, oh, this is great. They were very happy, and of course they never did. I think we only had 1 or maybe 2 of those meetings. But in any case, it was remarkable that these people, they really hadn't thought much about this coordination. And that was really one of the most valuable roles we played, was to help them coordinate. And so we did that. It's sort of illustrated in this manner. Here I've illustrated the 4 different ingredients to PSHA. You need to characterize earthquake sources, illustrated in the upper left there. You need to understand the earthquake activity on those sources via a magnitude recurrence relationship, illustrated in the upper right. You need to understand the ground motion generated by the sources in the lower left. And you need to put all that together in a seismic hazard analysis, which is indicated in the lower right. And so I've sort of indicated there with the logos, basically the kind of roles that we got the various agencies involved. And in addition, the ANU and ITB, as well as GA, of course, were sort of across all of those. And then PUSCEN, eventually, which was a great thing to see, this collaboration that we started, I think it's fair to say, we initiated with this project, has now been formalized into this National Center for Earthquake Studies. So all of those technical agencies are now part of that National Center for Earthquake Studies, which sits underneath Public Works. And to cut a long story short, I'm not going to go through the historical development of earthquake hazard maps in Indonesia, but they've evolved considerably in the last decade. The first one in 2002 really only considered the subduction zones. It just had broad swaths of red where there were subduction zones and pretty low hazard elsewhere. But since we started with the more sophisticated maps in 2010, and now this one, which is the 2017 seismic hazard map for Indonesia, they've gotten a lot more sophisticated, and in particular included many more active crustal faults. Let's see. So you can see things that you expect. You expect the hazard to be very high in the subduction zones and great away from them. We always expected, of course, that there would be hazard along the Sumatra fault. And really, we would have known in Papua also that you'd have some very high hazard along these active plate boundaries, as well as along the Palu Koro fault. What is really doesn't really stand out in this is probably the most important factor, and that is Java. But Java now includes a number of active crustal faults. There's some that stretch through here. I'll show them to you later. The Opak River fault here, and another Kendeng thrust through here that have really dramatically increased. Although it's not that evident when you look on the full national scale of the hazard map. It doesn't really stand out. It really has increased by a factor of 2 or 3 at least in most parts of Java. And this is really important because that's where all the people live, that's where the major cities are. So it's really this that is the controversial part of the hazard map. And in fact, there has been as few, it's interesting, we have the opposite problem with Australia, in that the hazard's gone up and the engineers are sort of, very uneasy with that. But I think it's the correct way, I think this is far more accurate. Very important to consider these crustal faults, as I'll illustrate in subsequent slides. Another interesting thing that I wanted to point out is Sulawesi has very high hazard. It's got a number of active plate boundaries running through it. This Palu Koro fault is a major, where's my pointer? Is a major strike slip fault, and it runs through right through the city of Palu. Palu is located in a sort of basin, a really elongated basin that's elongated right along the fault. And although it's not one of Indonesia's biggest cities, it's one of its fastest growing. And the whole city is situated right along this fault zone. So it's actually a potential hotspot for seismic risk. So in terms of the actual impact earthquakes might have, they could be very high in Palu. The Palu Koro fault is thought to be slipping at 4 to 6 centimeters per year. So very rapid slip rate, and that whole city is located in a sedimentary basin. So very high potential. Oh, and the red there, you maybe can't see that, but that's 1G that is 1G at a 10% and 50-year recurrence interval. So that's extremely high hazard for that area. And it's, as I say, it's got one of Indonesia's fastest growing cities right there in that 1G area. As I mentioned, people who live in these areas don't necessarily realize that they're an area of high seismic hazard. This is a figure from a GA record that is now being submitted by Jonathan Griffin as a BSSA article, which looks at historical accounts of earthquakes during the colonial period in Indonesia, and in particular in Java. And what you see there is these circles. You can see these circles are what we've inferred to be the Mercalli intensity of these observations of shaking. And you can see 8 is where buildings start to collapse. And you can see there are a lot of those in areas of what today has very high population. So people in these highly populated areas have not felt this intensity of shaking for a few generations now. But clearly during the colonial period, they experienced very high seismic intensities, and that's going to happen again eventually. So even though people's experience of earthquakes is not, they don't think the hazard is that high, they really are living in a very dangerous area. So one of the things that we did then as part of this project, it wasn't just trying to put together some pieces of the science, but there was a lot of capacity building, and there was also an educational component to this. In particular, we worked with ITB to develop a graduate research program in earthquakes and active tectonics. This was seeded with Australian aid funding, but it was augmented by a number of Indonesian agencies, including the Department of Education. ANU directly assisted with supervision of 7 PhD students, and they also graduated 40 master's degree students, so we did some lecturing for those students, and we did topics like earthquake geology, seismological studies of earthquakes in the crustal structure, and tectonic geodesy studies of active faults, and also did some field work with some of those students. And that just illustrates one of the Indonesian lecturers, Danny Hillman, as well as Ashraf Kalali was one of the ANU lecturers. We also established what I call the Australian and Indonesian Tectonics Observatory. This was established with some money from the Research School of Earth Sciences as a major equipment grant, and it's basically a pool of geophysical instruments, seismometers, and GPS receivers. We currently have 40 seismometers and 6 GPS receivers. These are going to be co-managed by ANU and ITB through the 10-year lifetime of these instruments, and we'll be able to continue. Now this project is ending in June, but we'll be able to continue, ANU at least, will be able to continue working with them and running projects at very low cost, because these instruments are already there in Indonesia where fieldwork costs are low, and we don't have to worry about importing the instruments. We've already done quite a few, this is a very, very busy slide, quite a few experiments, but we've got, still got a network running in East Indonesia here. But we've also done tomography experiments, ambient noise tomography experiments in East Java, West Java, as well as some sort of site looking at basin effects in Jakarta, Bandung, and Palu. So we've already run quite a few experiments through the course of this project, but we'll be able to now run more in the future, we hope, if we can get a modest amount of funding. So some of the highlights of that were the AITO and its precursor instruments have been used in those seismic deployments I just mentioned, as well as 2 GPS campaigns and 1 aftershock study. That was of the PD earthquake. It's supported 7 PhD research projects, those same ones that we co-supervised. We've done high-resolution analysis of GPS measurements in eastern Indonesia and Java, and also done a very detailed study of the Jakarta Basin. And those are the ones I want to talk about in the next few slides. The first one is about the GPS campaign in eastern Indonesia, which we worked with mainly with BIG and ITB to make additional measurements out there. It's a very complicated tectonic region. There's a transition from classic ocean subduction in the west to continental collision, where the Australian continent is colliding with the cinder block in the east. And really, previous models of this really, there just wasn't resolution, it wasn't enough resolution to work out how that transition happened. There were a number of models for it, but it was based on very sparse data. We did a lot of work with BIG to try to dig up all of their archive data, because as you may know, for GPS measurements, you need measurements going back in time. So we helped them sort of dig out of their archive as much data as we could get, and then we made new measurements ourselves with them, and we were able to do at least a single repeat of those measurements. And those are in the end the set of observations we were able to come up with, which is much larger than what was available previously. And this is the kind of model tectonic model we came up with. We find that the convergence between the Australian plate and the cinder block, as I said, there's classic subduction here, so all of that, essentially all of the convergence, but not all, is accommodated at the Java Trench on the megathrust. But as you move east into the area of collision, more and more of that convergence gets accommodated by this back arc thrust system here, which is called the Flores back arc thrust. It has been identified previously, but it seems clear to us that there's a continuous zone of this thrusting in the back arc that actually stretches all the way through to East Java. Even though the convergence there is very small, it's significant. And that is very important. It's also significant in terms of its potential impact, because that's getting into the densely populated island of Java, in particular Indonesia's second largest city of Surabaya. And that's what's causing that little blip, if you saw on the hazard map. There's sort of a little blip in that very easternmost part of Java, and it's due to the inclusion of that active convergence along the Kendeng thrust. We also think that there's a substantial tsunami hazard from this back arc thrust. My student Rian Prananto has been working on that at ANU, and we think, throughout that Flores Sea region, there's significant hazard due to these earthquakes. But we've also been working with one of the geologists there, Jonathan Pownall, who published this paper that really sort of crystallizes a lot of work that he's done with Robert Hall over the years, and really shows that what we thought was the tectonic picture in the easternmost Banda arc is not at all, true. It's often characterized as having that, I don't know if you remember that arc, that very tight arc with the subduction within about 200 kilometers. It flips around 180 degrees. And that's this part here, this arc, which many people regard as a megathrust and capable of hosting very large earthquakes. But you know, Jonathan and his work with Robert Hall and Gordon Lister have developed an alternative model for the Bond to Sea, in which really this is essentially a passive feature which has sort of a collapse feature. And what you have is this slab rollback, which is opening up very rapidly this Weber deep. And so instead, what the really active faults here are over here where you have some thrusting, and over here where you have a huge normal fault. And in fact, this Weber deep, the whole thing is effectively a massive normal fault scarp. So it really is a unique part of the world. You know, we've been working some with this to try to determine what kind of earthquakes might occur there, and there's really no analog for it. You really can't find Jonathan knows of some that, you know, geologic evidence for them, but there's no current analog for this kind of system anywhere on Earth. And we do think, Rian has done some work on the 1852 Banda tsunami, which has always been thought to originate as a massive earthquake on the megathrust in the eastern, this is the eastern part of the Banda Sea here, where there's that curvature which we thought was a megathrust. And so to get the kind of observations that we're seeing in this historical event, people had to put a huge earthquake on that megathrust. But Rian is finding that, in fact, the data are much more consistent with a considerably smaller earthquake on this Banda detachment, which is very important because it means it completely changes the picture of earthquake and tsunami hazard in the Banda Sea, and shows that, well, it shows that this kind of massive detachment fault is potentially seismogenic and tsunamigenic. So I want to move then a bit further west into Java, and I discussed how that convergence along the back arc here extends all the way into eastern Java and causes an increased seismic hazard in that area right near Surabaya. We subsequently did more work and tried to do a similar thing where we helped BIG dig up all their archive data and find as much GPS observations in Java as we could. And the conclusion of the analysis of that is that that zone of convergence actually extends all the way through northern Java. And you can actually sort of see that, where these are the GPS vectors with reference to the Sunda block. So you can see they're really small all along the northernmost part of Java. And then suddenly, when you sort of cross over into the central and southern part, you get much bigger vectors. So there's movement with respect to the Sunda block. And so the conclusion of this is that there seems to be active convergence along some kind of arc all through northern Java. And what was really interesting is that when we compared with what the geologists were finding for active faults, it agrees really well. They believe that there is a system of active faults that sort of extends through northern Java. There are some sort of discrepancies here which we still have to work out, but it seems to agree really well and is responsible for this raising of the seismic hazard in these densely populated parts of Java. And you can also see that some of these faults, there's still a critical problem here that some of these faults are pretty close to Jakarta, but if Ashraf's zone of convergence was much closer to Jakarta. So we've really got to work out whether we could get earthquakes closer to Jakarta or whether, you know, you would only get them on this Chimandiri fault over here. So this really brings up the issue of Jakarta and what kind of seismic risk it faces. Again, Jakarta has not really experienced a large earthquake all through the 20th century. There have been a few earthquakes on the south of Java that have sort of scared some people with a bit of shaking, but it's nothing compared to what was experienced in the 18th and 19th centuries, according to the work that was done by Annie Nguyen, who was she was an intern here, Jono, and worked very closely with Jonathan Griffin. And she worked up a lot of this data, and that's since been, as I said, submitted to BSSA. But for Jakarta, there were at least 3 historical events that really caused a lot of damage in Jakarta. These occurred in 1699, 1780, and 1834. And these appear to have caused very widespread damage and extensive damage in that area, which was then called Batavia. Annie did some work, Annie and Jana did some work on that. And the problem was you only had the reports of the shaking. You don't know what caused it. And so that's what Annie and Jana were looking at. And the determination was that we think the 1699 was caused by a very deep intraslab event just beneath Jakarta. and that these other 1780 and 1834 might have been caused by crustal faults relatively close to Jakarta. So in any case, even if this is wrong, Jakarta has experienced shaking that's similar to what you would get from earthquakes on these faults. It's experienced that in the past. So we have to really look into that and be very concerned about Jakarta, which the greater Jakarta area has 30 million people, greater than the population of Australia, all sort of crowded into that one area, which is also lies on a sedimentary basin, a deep sedimentary basin. So you can see this is where Jakarta is located here. And this is a geologic map which shows that it's the whole basin, all of Jakarta is basically sitting on alluvium or dunes, paleo dune systems. So it's all on very soft sediments. And in fact, beneath that, there's some volcanic tuff that's also relatively soft. So there's a high potential for seismic amplification in this area. And we did a deployment here, as I showed with the Australian instruments, and did a ambient seismic noise tomography study. And you can see the kind of record section we were getting here. So these are surface waves that are produced from just the noise recordings. We can do some processing of those noise recordings and essentially produce records, the kind of records that would be produced if there were an earthquake. In this case, at this station located in the northeast, we can sort of produce the kind of records we could see if there had been an earthquake there and look at what would be observed at the other parts in Jakarta, and we can use those records then to derive the seismic structure, the shear velocity structure of the Jakarta Basin. And that's what's indicated here. This is along a south-north cross-section through the Jakarta Basin, and you can see that indeed it has very low velocity sediments, less than about 1 kilometer per second, that persist down to about 500 meters depth. And according to the ambient noise study, as you go from south to north, it gets deeper overall, and there's this sudden increase in depth right in the middle of Jakarta. We subsequently, my student Chipta, Athanasius Chipta, he's from Badan Geology, though, with a geological agency there. He did a study also using seismic noise, but in a different way, which has somewhat higher resolution. And he obtained this kind of model, which agrees remarkably well with the ANT result, given that we expect this to be a smoother result just due to the nature of the data. Very, very low velocity sediments to at least 500 meters depth, and in the north, it goes down to below, close to a kilometer depth. So very deep, very low velocity sediments in that basin. That's a real problem, as we saw in the recent earthquake in Mexico City in 2017. That's been well known for the Mexico City basin, and that's where most of these figures are from. Oh, I didn't list the reference for this. But what happens is when seismic waves enter soft sediments, they get amplified. This is just essentially due to conservation of energy, that it takes more movement for the same amount of energy in soft sediments than in hard sediments. But the other thing that happens is you get what's called basin resonance. So these amplified waves bounce around in the basin, and they will cause resonance at certain frequencies, characteristic frequencies that are characteristics of the structure of the basin. And that's very well known in Mexico City. In 1985, there was a large magnitude 8 subduction zone earthquake that occurred 400 kilometers distant from the city on the subduction zone. And you can see here the records from that. You can see you got 150 centimeters per second in velocity right near the coast, right near the earthquake. And then as you go farther away from the earthquake, it gets much smaller. It's gone down to about a factor of 10 as you get up into this escarpment here. But then suddenly, as you get into Mexico City, the amplitude increases. It's gone from 18 centimeters per second to 35. And then as you get into the basin, it's gone back up to 170, which is even greater than the ground motion right near the coast. So there are very pronounced effects, amplification effects in Mexico City, and this has long been recognized as the resonance effect of the lake sediments in Mexico City, in the Mexico City basin. And this, in the case of the 1985 earthquake, this caused severe damage to tall buildings because that resonance effect, as you can see, it affects sort of longer periods, maybe 2-second period waves, and so that affects higher buildings. We'll have a look at that later. But that affects taller buildings, and many of these collapsed during this earthquake. 500 buildings were destroyed, 8,000 deaths were caused. So it was a devastating earthquake, even though it was 400 kilometers, quite a long distance from the subduction zone. And let's bear in mind that Jakarta is about 300 kilometers distant from the South Java subduction zone. So Cipta proceeded to try to look at what the basin effects might be, and he did some numerical modeling of this. This was the type of model he used. This is a south to north section. This was a very computationally intensive simulation, and so we had to restrict it to 2D to be able to do it. Here you see a cross-section through Jakarta going from south to north. This is the megathrust, so this is the subduction zone here. This is Jakarta here. This tiny little sliver is the Jakarta Basin. You can see it's been blown up there. So this is the low-velocity Jakarta Basin. And we also considered a big megathrust earthquake, magnitude 9, as well as a crustal fault and an intraslab earthquake. We considered those three scenarios, and this is the kind of thing we got. This is the crustal earthquake. This shows the waves coming through, and you can see these are the surface waves coming through and how they get trapped in the basin there. So you can see that, and they're just sort of bouncing back and forth within the basin. And you can see here the seismograms that would be recorded. The green ones are hard rock, so they're relatively simple and low amplitude. The blue ones are what happens if you put in this low velocity basin. So you can see they're much larger, longer duration, larger amplitude, much more complicated waveforms. You can see that the amplification is about a factor of 2.5, I think, for the peak ground velocity. For certain periods, it will be much higher, but for peak ground velocity, it was about an amplification of 2.5. So we get considerable amplification as well as increased duration of the ground motion in the Jakarta Basin. And this could potentially, this resonance effect can potentially affect tall buildings. This is from the Mexico City earthquake. If you look carefully, you can see this swaying, you can see the curtains in there swaying back and forth. So the whole building is sort of moving back and forth. And what you see happen in just a second is you'll get total collapse of that building. Bang, the whole thing just collapsed. And this, because the resonance in the Mexico City basin is roughly 2 seconds, that will tend to affect things like 10 to 20-story buildings. This might have been actually, yeah, this was due to the Pueblo earthquake, which did excite shorter period, somewhat shorter period resonance. So that might be a 4 to 6-story building with maybe half a second resonance. And the problem is that resonance of the basin is matching the resonance of the building. So you get complete collapse because of that matched resonance. Now in the Jakarta Basin, we get about a 5 to 6 second period for the resonant period of the basin, the major resonant period of the basin. And that would affect much larger buildings, 60-story and above, roughly 50-story and above buildings, of which there are many in Jakarta. There's at least, I think it's 14 of those buildings in Jakarta, and many are planned for the future. They're planning 100-story buildings in Jakarta. Those have been approved and are planned to be built in the next decade or so. So we think that this resonance potentially has very profound implications for that kind of construction in Jakarta. The thing we have to do now, and it's going to be very difficult because we don't have any more funding, is what the Indonesians have to do, I should say, is they have to move from hazard to risk. The hazard will be used in the building code. It'll be used to establish a building code that will require buildings to be built to withstand the kind of shaking we expect. But that code really isn't applied. It's applied for buildings 8 stories and above, but even then it's not uniformly applied everywhere in Indonesia. So we really have to increase the application of that building code. And I've been really pushing my colleagues there to try to do that. And the way to do that is to influence policymakers, obviously. And the only way to do that, as we know at GA, is to frame things in terms of risk. Talk about, not about the level of shaking that might happen, the 0.2 or 0.4 G. You have to tell them how much money it's going to cost and how many people are going to be killed by earthquakes. And that's really what the Indonesians, I think, have to move to if they want to influence policy and get this building code applied more widely. And so we've got to start on that. Garup is here in the audience somewhere. He's working on seismic risk. This is our first very preliminary estimate of seismic risk in West Java. I'm not going to talk about the numbers because I'm still not all that confident in them. But this is trying to plot here is average annual loss due to earthquakes in Indonesia. And so we're going to try to firm up these numbers, and they're going to have to work much more closely with the global earthquake model because that's what these people do. They're very keen to work with the Indonesians. The Indonesians are very keen to work with them. So we hope that this project, even though GA's involvement will end in June, that it's going to move forward, and they're going to be doing not only probabilistic seismic hazard, but also probabilistic seismic risk. And by doing so, they'll finally be able to influence policymakers and get much more wide application of the building code. So look, these are some conclusions. These were actually written for the DMI presentation I was giving. But these are some of the main things that we've done. And we've managed, I think, to help the Indonesians educate a new generation of Indonesian earthquake science specialists. We've greatly raised the rate of publications on Indonesian earthquakes during this period of the project. There are a lot of publications that are still being prepared and have been submitted. That's very important for them because they need to get that, just like we do, in order for their science to be credible to their policymakers. They need to show that they're publishing in peer-reviewed journals, just like we do. And also, we've undertaken some very important, I think, earthquake science that has helped identify and estimate slip rates. Very difficult to do this still in Java. You would think with the much higher slip rates it would be easy, but there's also higher erosion. There's a lot more cultural disturbance of the faults. So it's actually similar problems that they find it very difficult in some cases to estimate slip rates on their faults. We've mapped crustal structure that helps identify active tectonic structures and helps them map and more precisely the earthquake activity. And we've developed models for basin response that can be used to model seismic wave amplification and resonance. And we hope to continue some of that work as a sort of ANU-ITB collaboration. Prospects for the future. Well, ANU and ITB there are actually, I guess I should give the bad news that the prospects for the future are not good for the GA component of the program because DFAT has decided to discontinue that. They've really, as we all know, have had some very severe budget cuts over the past few years, and they've decided they just can't support this despite the fact that all of the stakeholders, I think all of the stakeholders, really wanted it to continue. But ANU and ITB have established a new split-site master's degree program, so those educational links that have been started by this project will hopefully continue. That looks very likely to attract support from Australian awards as well as a big fund in Indonesia called LPDP, which is a fascinating thing, actually. It's written into Indonesia's constitution that 20% of their budget goes to education. And they can't spend it. So they made this big fund, which is called LPDP, out of which they're funding some of these scholarships, which hopefully will fund some of our students. We're also working together to support New Colombo planned study visits by ANU students. We had our first visit in April, and we hope to do that over the next few years. The instrument pool, the AITO instrument pool, has resulted already in collaborations with overseas institutions. So already, we've done some of the projects that were funded by the Indonesian project, or the DFAT-funded project already, but already this is attracting interest from overseas projects, like one from Cambridge University, which will look at crustal structure and seismic hazard in Kalimantan and Sulawesi. There's also a USGS peer proposal to study the volcanic system of Mount Agung in Bali, which we all know has been very active recently. So this is already attracting a lot of interest, which is what it was designed to do. Once we have the instruments there, we think that we're going to be able to work with a lot of people that can bring in resources from overseas. And then finally, ANU will be submitting further proposals to the Australian Research Council and RISTEC, which we'll be working on with our Indonesian colleagues. And that's the end. Thank you very much.